Yesterday, right?
Yes, sir.
I think we have done the Thevenin's theorem or Norton's theorem, right?
Norton's theorem.
Yeah, okay. Look at this. This one. I have some fever as well, so and some technical difficulty. That's why it's a bit late. By the way, can you see the screen?
Yes, sir.
Yes, sir.
Well, I think we have done this one as the Thevenin's, right? Before.
Yes, sir.
Okay. Let's do the same thing. Like find the current through the 50 ohm resistors by using the Norton's theorem. So let's do the Norton's theorem. By using the Norton's theorem, let's solve this to find out the current go through the 50 ohm resistance. We have done the same thing by using the Thevenin's theorem. Let's do it by using the Norton's theorem. Okay, let's start. All of you. Remember one thing, that we are almost finished chapter number 1, and I will give you the first time exam schedule very soon, because today is 31st. So hopefully next week will be your, obviously next week will be your first written exam and first exam viva. So let us finish this chapter 1, because we have to also discuss about other 2 chapters, chapter 4 and 5, which is included in the first term exam. So maybe we will finish our
Interesting.
Done, sir.
Done. Okay, wait.
Yes.
Rest of you, how was it?
Done, sir.
Done? All of you? Rest of you?
Yes, sir.
Done.
Right, my network is really unstable. Okay. So we have tried this one. Okay, what is the let me draw. That is your circuit, right? So if you find the Rn, what is the Rn? So if you remove,
Sir, 121.4035.
so you need to find the Rn from this side. And then make it short. So what will be the equation of Rn?
R1 plus R2.
1. Why 1?
R1.
Oh, R1. Tell me the values.
The 121 point.
No. Values, the equation. Value of R1 at
30 ohm plus 40 ohm.
30 plus
40
40
parallel with 500.
parallel with 500.
Then with series with 60 ohm.
That is at 60. Is that the same for all of you?
Yes, sir.
Yes, sir.
Yes, sir.
What is the result?
121.
121
120
121.4035.
4035. Hopefully it is the same answer to all of you. Okay, so for the IN, sorry, to find the IN, we need to do that is our IN. So we need to find out the I first, right? Total current I. So our equation will be, what will be the equation of IN?
I into
I into
R3 by
value.
Sir, 500 divided by 500 plus 60 ohm.
500 plus 60. Do you agree, all of you?
Yes, sir.
Okay, so for value of I, it is V by RT. We also don't know the RT. So what is the equation of RT?
There are 60 parallel with 500.
60 parallel 500
Then with series with 40 and 30 ohm.
series with 40.
And 30 ohm.
Is it the same to all of you as well?
Yes, sir.
Yes, sir.
What is the answer value of RT?
123.5714.
123.5
5714.
5714. Then what will be the value of I?
1.6185.
So what is the value of V?
200.
200 divided by 123.5714. And the result is
1.6185.
6185 ampere, correct? And about
Yes.
the IN, what is the value? Total
IN is
result?
1.4452.
Is it the same answer to all of you as well?
Yes, sir.
Any other results or any other values you have? Anyone? Anyone?
Sir,
Result? Huh?
sir, IN is equal to I into Rn divided by Rn plus RL, isn't it?
Which one? IN equal to?
Sir, IN is equal to I into Rn divided by Rn plus RL, isn't it, sir?
No, 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 no. No, we are finding out the IN, the current divider rule.
Oh,
Yeah.
yes, sir. Yes, sir. Okay, sir.
Current divider rule. By the way, none of this is actually our answer, right? We just find out the equivalent circuit, right? So our equivalent circuit will be this is RL, this is RN, and that is our IN. So we already have the value of IN. We already the value of Rn. If you just put these two values here, then we can easily find what is the current go through the RL. The value of RL is 50, right?
Yes, sir.
So by using the current divider rule, you already know what is the total current. By using the current divider rule, you can easily find out what is the current go through this. Let's say this is I2. Let's say this is I1. So you can find the current go through the I2 because that is the question.
Yes, sir. I also got that.
Okay, so what is the value of I2? That means through the RL.
Sir, I into
Yeah, I into
with,
RN,
I
RN.
Rn divided by Rn plus R2.
Yeah, okay, so what is the result?
1.00236.
0.26. So that is actually our answer, right? That is our answer. Is it the same to all of you?
yes, sir.
Yes,
Yes,
sir.
sir.
Oh, we are almost 31, or not almost 31 students, but how about the rest of you? I can hear you only like 4 or 5 students. How about the rest of you? Remember one thing, that if you think that it is very easy, if you just watch what we are doing, it will be difficult for you, especially during the exam and also in the Viva. So please make sure that we do it together. Otherwise, you might have some problems. So please do it with us so that you have a very good practice. Do you actually really do practice at home or anywhere, or no? Not at all, right? Do you study at home? No? None of you study at home after the class, after or before the class, or outside the class. So how you can expect that without studying you can get a good grade? By cheating?
No, sir.
Then previously you have excuses that you have a lot of classes, you have a lot of things. This semester you don't have a lot of things. Normal semester. And you are already habituated with this online classes. So that is the problem. That is the problem. You want to do nothing, but you expect everything. Anyway, please study at home. All right, please study at home. Don't give any excuses. If I want to give excuse, I should cancel today's class because I have really, really bad fever. It is very difficult to wake up because I have a lot of fever last night. Couldn't sleep. Still, I can give you the excuses. I told you I don't like excuses. I don't give excuses. So please, it's a bad habit. Seriously. Okay. So, any questions so far? Remember one thing in this chapter number 1. Let me show you. In this chapter number 1, we have a lot of maths, especially okay, let me share my entire screen. So in this chapter number 1, we have done a lot of maths. If you do all those maths, whatever we practiced so far, I think from the very beginning, how many maths you have solved? 10, 15? Almost.
Yes, sir.
Different.
Problems.
Huh?
Sir, we have solved so many problems.
Yeah. So during the class, online and on-campus classes, so many different circuits, although they are simple, some of them are slightly difficult, but we have discussed so many already from the exercise, from outside, from the example. So if you do them well, properly, I hope there will be no problem in your, not only your exams, but also your other courses, because you know that all the courses are related to each other. Fine. So because chapter number 4 and 5, which is the next one, there is no math. Let me tell you, in the whole course, entire course, only three chapters has math. Chapter 1, chapter 6, and chapter 8. And most of the math is actually in chapter 1. If you can remember from the very first week, maybe not first class, second class, maybe third class, that we have started do the math every time till today, because these are very basics for this course. So I hope you have a very good idea about the electronics, especially the basic part of the electronics, so that you can solve the problem. All right, because it will help you in the next part of your study. By the way, did we discuss about the Kirchhoff's voltage law and current law, right? Do you remember? Kirchhoff's voltage law and Kirchhoff's current law? Because it will be needed. Problem is those kind of laws you cannot find in this book. All right, so whenever you try to study, you cannot find it here. You need to find it from your reference book or other book, or maybe from internet. So please be very sure that you can do or can use those laws, especially two Kirchhoff's law, Kirchhoff's voltage law and Kirchhoff's current law. Right? Okay. In this, although still in this chapter, we have one more.
Sir.
Yeah.
So based on Kirchhoff's current law and voltage law, if you take any review class, it will be better, because during this time my course didn't end, and I think maybe there are many people that their course that time not added.
Oh, okay. Yeah, fine. Let me just give you a very brief idea, very quickly, which is so if you have any, according to the Kirchhoff's current law, you know that if you have a junction, of current flow, if it is I and if it is I1 and if it is I2, let's say this is the junction, then according to the Kirchhoff's law will be I equal I1 plus I2. That means incoming current. You always remember that Kirchhoff's law is used in this kind of what is it? Junction. So incoming current for any junction, for any junction of a circuit, incoming current is equal to the outgoing current. So I is incoming current, look at it is incoming, and I1 and I2, they are outgoing current. All right, so you can say in this way that incoming current of any junction is equal to the outgoing current. This is one way to explain. Another way to explain is in any junction, the total summation of the current is 0. For example, you can rewrite this equation by this. We can write this equation by in this equation, right? So,
Yes.
Yes, sir.
so in any junction here, let's say this is a junction, the total amount of current is actually 0. So that's why, because I1 minus I2, I1 minus I2 equal to 0, because these are negative because their direction is different, because one I is incoming, I1 and I2, they are outgoing. That's why they are different. They have different direction and different values. That you also can write this equation in another way, like this. We can write this one as well, right? I1 plus I2 minus I equal to 0. So if you think that I1 and I2, they are positive, so I should be negative, opposite side. So you can also write the same equation like this. So you can explain the Kirchhoff's current law in this way. Fine?
Yes, sir.
So there is Kirchhoff's current law. If you think about the Kirchhoff's voltage law in any closed loop, this is a closed loop. This is a closed loop, so Kirchhoff's voltage law is used, or the Kirchhoff's voltage law is true in any closed loop. So this is a closed loop. So according to the Kirchhoff's voltage law, the total summation of the voltage of any closed loop is equal to 0. For example, V minus IR1 minus IR2 equal to 0. Because if you think about the voltage drop here in R1, it should be V equal to IR. I is equal to I, R1, R equal to R1. So that's why I over 1. In this case, voltage drop is IR2, and this is our voltage. Why they are negative? Because they are dropping the voltage, reduce the voltage. That's why they are negative. So all the summation is actually equal to 0. And that is the Kirchhoff's voltage law. That means in any closed loop, the total summation of the voltage is 0, and it is true for any closed loop. If you have another closed loop here, you have another closed loop like this. What will be the equation? Let's say this is R3. What will be the equation in the second loop? Anyone? Anyone? What will be the second equation by using the Kirchhoff's law? Huh? No one? Try. Come on. Anyone? Whoever actually asking, can you answer? Miss Fuza?
Sir, because of net problem, I didn't listen what you explained this.
Oh, I said I was asking that what will be the equation for the second loop? I was asking what will be the equation of second closed loop. This is a second closed loop. Look, this one.
Sir, V minus IR1 minus IR3.
V minus IR1 minus
IR3 equals 0.
IR3 equal to 0. Yeah, correct. So that will be the Kirchhoff's voltage law in the second loop. Remember, Kirchhoff's voltage law is true for all closed loop in a circuit.
Sir, what about R2?
R2 is in the first loop.
So why it isn't included in second loop?
Look how the current will flow. First, the current will flow from, let me show you. First, the current will flow in this way, right? That is the loop, right?
Yes, sir.
Second one, this way, right?
Yes, sir.
So in the second loop, is it R2 is involved?
No, sir.
So that's why. Yeah, fine.
Yes, sir.
Yes, sir.
Okay. Okay, fine. Okay, any other question? So as I said that in the chapter number 1, those theorem and those rules or those technique we are going to use not only for this chapter but also to the other chapters as well to solve the math. So please make sure you know it very well. I'm supposed to solve this one as well, this math, but not this time, maybe this one. I have done this one in the previous semester. Although look how many registers we have. 1, 2, 3, 4, 5, 6, 7, 8. What do you think about this one? Look at it.
It's interesting.
Interesting, right? Interesting. And do you think it's difficult? It is difficult, right? If you don't do it step by step, or if you don't do it properly, it is difficult. Let's say, look at the question. Calculate the current in the 50 ohm resistance. This one, that is our RL, in the network shown in figure 1.34, this one. So it is asking what is the current go through this 50 ohm resistance. What will be your plan to solve this?
Thevenin's theorem. Thevenin's theorem.
Thevenin's theorem. How? Look at the number of resistors. This is RL. So if you want to Thevenin's equivalent voltage, you should find out the voltage here, right? Look how many resistors you need to consider. Look how many current is divided, how many times current is divided, 1, 2, 3 times. Any other idea? Actually, I have solved this one in the previous semester. So,
Sir,
yeah.
Sir, first we can find voltage across 80 ohm, and then we can find voltage using same method across 60 ohm. After that, we can find current for 50 ohm. We can divide the circuit into 2 parts.
Yes, correct. We actually not 2 parts, 3 parts actually. X, Y, Z. You can see that in the main technique to solve this problem is as this is a very complex one, as there are so many components we have in this circuit. So if you go in conventional way to solve this one, it will be a little bit difficult or complex. So to minimize the problem or to minimize the complexity, what we can do, we can divide this circuit into 3 different parts. You can see there is a called X. So the main technique is we are going to divide the circuit first into 2 parts. You can see the X on the left side of the X, on the right side of the X. So on the right side of the X, all of the resistors will consider as RL. And on the left side of the X, we will consider as our normal circuit. Fine, do you understand? So if you consider all the resistors on the right side of the X as RL, what we can do to find the E0 and R0? Very easy, right? We remove all of the resistors and only it will be these 2. Then it will be quite easy, right? Like this. Like this, look. This was the X. Previously, on the left side of the X, we have these 2 and this. And after solving it, we have only 1 and only 1 voltage source. That means we reduce 1. That's how we solve this one. After doing the X part, then we use another part, which is called Y. So on the right side of the Y, we will consider as RL. On the left side of the Y, we consider as our conventional method. So we remove the RL, all these 3 on the right side of the Y, and then and find the E0 and R0 again. And this is it. Look at the left and right side of the Y. Now it is reduced on the left side. Look, on the left side of the Y, we have 1, 2, 3 resistance. Now after doing this, we have only 1 because we have only 1 R E0 and R0, like this, E0 prime and R0 prime. Right? So, and after that, you also can do by using the Z here, or you can do it directly, no problem, up to you. But here they have divided it again, Z, and then they have solved it. But if you don't divide the Z, I think we have done this one before, just before the first example we have done. Almost,
Yes, sir.
almost similar. If you don't consider the Z, so you can do it by considering Z or by not considering Z. Now, after that, that will be our ultimate equivalent circuit, and then we do find out the E0 and R0. After that, that is the equivalent circuit. That is the equivalent circuit, and then we can find easily what is the current go through 50 ohm resistance, and that is the answer. So I equal to V by R, this one plus this one plus this one. Right? So this is a new technique. So you need to know a lot of techniques to solve the math. So it is now up to you which technique you are going to use to solve the circuits. Right? Fine, any question? Feeling a little tired. Any question? No? From the next class, we are going to start chapter number 4 because we have already done chapter number 1. Chapter number 4, very easy theoretical thing. In the meantime, I'll be strong enough to discuss. So chapter number 4 will be atomic structure, very easy. All about theory, and you know all the theory very well already. Should not be a problem. Okay. So if there is no question, let me give you the attendance. Connect. Tab direction is unstable. Why? Okay, so please response. MD Shuman Rana. Shuman Rana. As Mustaqib. Binoy Krishna. Ashraf Hussain. Ashraf Hussain. Sonia Akhtar.
Yes, sir.
Andhaka Tanvir.
Yes, sir.
Marjia Rahman.
Present, sir.
Mahfuz Akhtar.
Yes, sir.
Sadiqul Islam.
Yes, sir.
Fatur Rahman. MD Ali Danim. MD Ali Danim. I saw him. Sultan Rajia.
Sir,
Present, sir. Sir,
Yali Donim
Yalit
was
on
present.
him.
He got disconnected.
Okay.
Sir, Sultan Raji is present.
Okay. Rubel Babu. MD Sajid.
Present, sir.
Leader Al Mahmoud. Rabab Khan. Abdul Shabur.
Present, sir.
Noshin Anjuman.
Present, sir.
Sharafur Rahman. Sharafur Rahman. Mehdi Hassan.
Yes, sir.
Mehdi Hassan Medul.
Yes, sir.
Ashraf Mahmoud.
Yes, sir.
Noshin Afifa.
Present, sir.
Mahbub Alam.
Yes, sir.
Imrul Hassan.
Yes, sir.
Ashikur Jamal.
Yes, sir.
Sadia.
Present, sir.
Dolan Bishash.
Present, sir.
Najmul Saqib.
Present, sir.
Mahi Mawshed.
Yes, sir.
Abdul Rajak. Abdul Rajak.
Sir,
Tawhid
Nazmul Saqib.
Yeah, Najmul Saqib. Fine. Tawhid Ahmed. Tawhid Ahmed absent. Munurufa Afim. Asfim. Hassan Arafat.
Present, sir.
Shamin Akhtar.
Present, sir.
Shaukat Hussain. Ono Hussain. Ono Hussain. Samantha Jaman.
Yes, sir.
MD Shari Hussain.
Yes, sir.
Okay. Anyone else?
Sir, Sharafur Rahman.
What happened, Mr. Sharaf?
Sir, my mic wasn't working. Earphone mic was.
Anyone else?
Sir, Yali Donim. Sir, I got disconnected.
Yeah, I give you. It's all right. Okay, anyone else? No, maybe not. Okay, thank you very much, all of you.